Could you quantum tunnel through a wall? Subatomic particles routinely walk through walls, and technically, so could you just don't hold your breath for 10 circumflex? 40 years could you quantum tunnel through a wall? It's a question that sounds like something straight out of a science fiction movie. A thought experiment that pushes the boundaries of our everyday understanding of reality. The idea that tiny particles like electrons could seemingly pass through solid objects, city a concept that's actually incredibly well established and rigorously confirmed by countless experiments. Let's start with the basics. Because the quantum world operates in ways that often defy common sense and our intuitive perceptions of how things work in the macroscopic world around us. Imagine throwing a tennis ball at a brick wall. It bounces back predictably, obeying the laws of momentum and energy conservation. However, if we were to observe an electron, a subatomic particle that is far smaller and lighter than a tennis ball, interacting with that same brick wall, the outcome would be drastically different. Instead of bouncing back, there's a surprisingly high probability that the electron would simply vanish from one side of the wall and reappear on the other side as if it had tunneled through it. This isn't about breaking through the wall, it's about a fundamental change in the way we describe the electron's existence at the smallest scale. Quantum mechanics, the theory that governs the behavior of particles at this level, tells us that particles aren't always confined to a specific location. Instead, they exist as a fuzzy cloud of possibilities described by a mathematical function called a wave function. Think of it like this before we measure the position of the electron. It's not in one place but rather spread out across all possible locations, simultaneously existing in multiple states. A concept that Einstein famously called spooky action at a distance. The wave function represents the probability of finding the particle in any given location, and this probability isn't zero. Even when the particle encounters a barrier like a solid wall, the wall in this case isn't an impenetrable obstacle, but rather a region where the wave function has a non-zero amplitude, meaning there's a chance the particle's wave function can extend through it. This probability, however, decreases dramatically with the thickness and density of the barrier, which is why it is incredibly rare for electrons to tunnel through thicker walls. Now, let's delve a bit deeper into the mechanics of quantum tunneling, which involves a little bit of probability and a whole lot of weirdness. The particle doesn't actually pass through the wall in the way we traditionally think of it. Instead, the wave function briefly penetrates the barrier, and there's a chance the particle's state will be altered on the other side. It's like a momentary disruption of the particle's position, a fleeting connection between the two sides of the wall, allowing it to effectively reappear somewhere else. Scientists have demonstrated this phenomenon using incredibly precise experiments, measuring the arrival of electrons on the other side of walls with remarkable accuracy. These experiments have consistently shown that quantum tunneling is a real and measurable effect, not just a theoretical curiosity. So, could you, a human being, quantum tunnel through a wall? The short answer is theoretically yes, but practically it's an undertaking that would require a time frame so extraordinarily long that you are likely to have passed away before it occurred. The probability of a macroscopic object like a human tunneling through a wall is vanishingly small, estimated to be around 1 in 10 circumflex 45, a number so large that it is essentially zero for all practical purposes. To achieve a significant probability, you'd need a wall made of a particularly thin material like a single atom, and you'd need to spend an absolutely unfathomable amount of time attempting to tunnel through it. Let's put some perspective on this incredible number. Psi, the age of the universe, approximately 13.8 billion years, is a far smaller quantity than 10 circumflex 40. The energy required for a human to tunnel through a wall would also be immense, far exceeding anything we can currently generate or control, further decreasing the probability to an almost negligible level. Think about it like this: every single quantum event is fundamentally random, governed by probabilities, and the conditions required for a human to tunnel through a wall are so exceptionally rare that they are almost impossible to replicate. Despite the incredibly low probability, the concept of quantum tunneling highlights the strange and counterintuitive nature of the quantum world, revealing that our everyday notions of space and time may not apply at the smallest scale. Yet it forces us to reconsider our understanding of reality and to appreciate the profound implications of quantum mechanics. So, while you probably won't be spontaneously appearing on the other side of your bedroom wall anytime soon, the fact that quantum tunneling is a real phenomenon demonstrates just how remarkable and mysterious the universe truly is. The exploration of quantum mechanics continues to push the boundaries of scientific understanding and inspire awe at the elegance and strangeness of the fundamental laws governing our existence.